This is question 7, the last question in paper 4-1 from the June 2020 mechanics exam from Cambridge International. Up the top right of the screen you'll find a card that'll bring you to the playlist that has all my solutions for the questions in this paper. And below the video you'll find a link to an image of this question so you can attempt it on your own time before looking at my solution. As you'd expect from the last question in an exam, it is pretty hard. It's split into 2 parts. We're set with this overall problem where there's a ball on top of a hill. They tell us this is a smooth surface, this one, and it actually stays smooth the entire question. For part A though, this section here will also be smooth, and they'll change that in part B. Let's just stick with part A for now so I don't confuse everything. So we have a ball up here, we have a smooth surface, we have a smooth surface. We can also assume nothing changes between here and here. They tell us that the velocity stays the same, changing from this surface to that. Obviously in real life it would bounce or something, you wouldn't have a curve. It wouldn't work quite the same in real life. And then overall the first question they ask us to find the speed of Q. This is Q here and this one is P after these guys collide. They tell us a little more than that. They tell us that P after it collides will continue on at 2 meters per second. I think that's all we need. We have all the numbers, everything else here. So they're going to hit each other. This guy is going to continue on at 2 meters per second. What speed will Q be going at? That's pretty much what we're dealing with here. So we need to break this up into parts, and that's what you need to start thinking in your exam. Just do step after step. You know this is traveling 0 meters per second here. Find out what speed it's going at some other point. You want to know what it's going right when it hits this, really. But the first thing to find out would be what speed's it going when it gets down to here. So you're going to split this question up into a question about this. We have a ball, it's going to travel 2.5 meters. These meters are centimeters, meters. And it's what speeds are going to be down here. That's really now what the question becomes. This is 0.3 meters. So what would make the ball go down a hill? Gravity. Gravity is pushing down at 10 meters per second squared. So how's it going to affect this ball? So that's our first problem. And lots of students make a mistake here. We don't need all 10 meters. It's going down like this, not straight down. That's fine. Students understand that. They draw a triangle like this, 30 degrees, and they say it's going down 10 here, and they figure out what this number is. Sine 30 would be a half, so this would be 20 here. And they turn around and tell you that the ball must be accelerating at 20 meters per second this direction. But obviously that's clearly wrong if you think about it in real life. It's not going to travel faster this way than it would straight down with nothing in its way. So you would expect a number smaller than this, and that's because this triangle I've drawn here is wrong. It's not right. We actually want a right angle starting over here. This is 10. I want to find out what this vector is here. This will give us the right number. I'll keep the whole triangle up because that's 30, that's 90 degrees here now. Then this must be 60, and then this must be 30. And this is the triangle I want to use. I want to use right angle here, 10 down here, and I want to find what this vector length, the magnitude of this vector. I can see what the direction is. I've picked the direction to be down this way, but what's the magnitude of this? So this is just a simple trigonometric question. We have sine 30 is equal to this divided by this. So this length here would be 10 sine 30. Do that a bit slower if you need. Turn it into just a simple trigonometric question. Sine 30 is a half, so this is a 10. So really this ball will be travelling at an acceleration of 5 meters per second. Right, and that's pretty much all we need. We know how far it goes, we know its acceleration, we know its starting speed. You can use your equations of motion to do this. I don't like using equations of motion, although later in this question I'm going to have to. Well, I won't have to, but to save me a lot of time I will. This time I won't. I don't have to here. I know acceleration is equal to 5. Maybe I'd put minus. You know, I'll keep it as +5. We'll start at 0 to going up in time this way. So acceleration is 5. You always have to decide your signs, what direction you're going. Be careful about that. The velocity will equal 5t plus the initial velocity, in this case 0. We start at rest. And then displacement would equal, let's see, we get t squared, and then divide the 5 by that, plus, well, 0 to, doesn't really matter here. We just need the initial displacement. So what's the initial? We'll start the world at 0 up here as well, and we'll go plus 2.5 down to here. So that's 0 as well. We don't need this now. This is a slightly bit longer than using the equations, by the way. There's just one equation needed for that, but it's not much longer. I can find out everything about this world now, this simple world, until that little bend anyway. So what I'm interested in is what speed. Yeah, it's really just the speed I want to know when it gets to the end of this ramp. So let's see. I know the displacement. I know 2.5 must equal 5 over 2 t squared. Let's rearrange. 2 multiplied by that is 5. 5 divided by 5. I get 1 is equal to t squared. T is equal to 1. So after 1 second it'll take to go down here. So then the velocity is quite easy to find. The velocity, do I even need to write that in anywhere? V is equal to 5. After 1 second, v is equal to 5. So this ball at the bottom of the hill will be travelling 5 meters per second. 5 meters per second. So that's the first part. We've broken it up into this. Now forget that world. Let's start again. We're just left with this world. We have a ball travelling here at 5 meters per second. We have this guy going 0. And they tell us this is smooth. There's no friction. So if it's going 5 meters per second here, how fast will it be going when they hit each other? See, there's no forces here. There's a force pushing down, I guess, and the equal one pushing back. There's no forces stopping him or speeding him up or slowing him down. So he'll be going 5 meters per second. He'll be going 0. So what happens after the collision? This is the millisecond before, the instant before, the instant after. Well, the instant after, they tell us that, which one do they tell us? Let me see. P, the first one, is going 2. So what's this second one going? What speed's this second ball going? So we do that with conservation of momentum. We know before they hit, the first one, P, has mass 0.3, and it's moving velocity 5, and that's plus 0. This guy has no momentum, he's not moving. He has a mass, sure, 0.2 multiplied by 0 is still 0. That must equal the momentum afterwards. First guy is 2 multiplied by 0.3. Am I getting these masses correct? It looks like I am. Yeah, it looks like I am. 2 multiplied by 0.3, and the second one must be something, x multiplied by 0.2. These are all just simple numbers except the x. Just rearrange it. We will get x is equal, let's see, this guy minus this, 5 multiplied by 0.3 minus 2 multiplied by 0. Is that right? 3? Yeah, it is. Okay. And then we'll divide it all by 0.2. And if you put that into a calculator, you will get 4.5 meters per second. So that's the velocity of Q, I believe, unless I've lost track again. No, Q. The velocity of the second ball, Q. So that means the first one's going 2, and the second one's actually off ahead of it. So as time goes on, this one will get further and further ahead. Which is, you'd sort of expect if you think of a cue ball hitting each other. They don't necessarily have to. It depends on what weight they are, what speed they're going, different things like that. Could have different events, and which we'll see in Part B. In Part B, these balls are not going to travel at different speeds away from each other. They're actually going to coalesce. They're going to be the same ball. They're just right beside each other, moving in tandem, which you also see on a snooker table sometimes. Right, let me rub this out so we can start on Part B. I'll keep this general picture and I'll have to do a lot of work again. Okay, in part B, they change a couple of things. They change the fact that the second surface, the horizontal surface, is no longer smooth. It means it's rough. It has a coefficient of friction, which that's what they actually want us to find in this question. They keep this one smooth, so all the work we did there is fine. So if we can sort of forget that picture and turn it down into this picture. We have this going 5 and this going 0 still. But this time we're going to have some sort of friction F pushing against it. What else do they change? Oh, after the collision, we'll get to that, but after the collision these balls are going to stay beside each other and move as one. Okay, that should be interesting to us. Right, let's work on this friction then. To get friction, we need to know what kind of force is being pushed against the ball, up or down. You can write that either way. And that would be gravity multiplied by 0.3. So that's 3 newtons. 3 newtons. That means F, this friction here, this friction force, will simply be 3 multiplied by mu. So that's the force due to friction. That'll be good for us. Then, actually, I should probably step back a second and say, what are we looking for here? We're looking for these two balls hitting each other just before they hit each other and just after they hit each other. We can tell a lot about those instances. We can talk about conservation of momentum between these 2 points. So really, I just want to get to this point here, the instant before these hit. So I know what speed he's going here. What speed will he be going when he gets here? That's really what I want to find out. I'm not going to have enough. This is not going to tell me enough about it. Oh yes, that's it. I did this yesterday, so I'm trying to remember how I did it in the end. The information, we have to go all the way back to here. They tell us after they collide, they have mass of 0.5 because they're added together. They're moving as one, and their velocity is now 1.2. They're both traveling at 1.2. Before the collision, this guy's traveling at 0, and this guy's traveling, I don't know, x. So look, we can find out x, because before the collision, we have 0.3 multiplied by x plus 0, and that must equal after the collision. So let's put in an equals there, save me writing any more. We'll have x is equal 0.5 multiplied by 1.2 divided by 0.3. We can probably do this in our head. 5 times this is 6, or 0.6. 0.3 goes into 0.6 2 times. Do it on a calculator if you're not too sure. The speed here, they didn't ask us this, but we are going to need it. The speed just before collision is 2 meters per second. This took me a good few minutes to think through. Wait, how do I get it? I started over this way. I got into equations with mu, and I was like, well, I don't have enough information. Now you could do it that way and finally equate it to something here. But then I realized, it's much easier to start at the back and move up. So now we've got the speed at the end here. So now this question is really, forget about the ball that's holding still. I don't care about him. Let's just talk about the ball that's moving. He starts at 5 meters per second. Because of friction, he's going to end up moving 2 meters per second. Forget about the ball he's hitting. Forget about the starting up the slope. Now we're just down to this world. Sorry, I get very excited. There I am. So all we need to find out, there's 2 ways to do it. We need to find out is what acceleration is acting on this. Because if we find the acceleration, we'll find is equal to ma. We know what m is. That's that's 0.3 times a. So we can figure out the mu here if we know what the acceleration is. So we have an initial speed, we have a final speed, we even have a distance, 1.5 here. So we should be able to do this. One of our equations of motion will solve this. I'm just going to rub this out here. You guys can pause and look at it as much as you want. So I don't think I need to leave it there too much longer. So you can use one of your equations of motion. Probably the easiest way to do this. What I said earlier is I like to do it like this. I get something I know, like A. Problem is I don't know A. I guess A would equal 10 mu if you rearrange that. So you could get it like this. This is how I started to try and solve it. But No, I don't really know mu, so this is awkward, but we get phi is equal 10 mu t plus the initial speed. This is the big problem. Initial speed of 5, and then we get the displacement is 5 mu t squared plus 5 t, and we could say it's at 0. That's going to be awkward. You could solve it like this. You'll just end up having to find out what t is in terms of some messy mu over some mu here, mu plus some constant. It'd be a mess. It'd be an absolute mess. So you don't need to do it this way because we have the equations of motion. Which one? Let's see. We have a u. We have an initial speed. We have a final speed. We have something with acceleration in it because we want to know what mu is after all. We have a distance. So which one is that? I had to edit out searching for my notes because I don't memorize these ones too well. This one here would work. Phi squared is equal to u squared plus 2as. If we go ahead and use this, the final speed of 2 squared is equal to the initial speed of 5 squared plus 2. Now a is a bit awkward. Let me leave a out for a moment there. The displacement of 1.5. We're traveling this way. Acceleration is stopping us. It's working against us. The force, the resistant force is working against us. So the acceleration is a minus. Be careful of that. 10 mu. These are all just numbers except for mu. I can just rearrange this. We get a 2 squared minus 5 squared divided by 2 multiplied by 1.5 multiplied by minus 10. This will be a minus number. This will be a minus number. That'll give us mu. And if we put all that in, I can't see it on my notes, but I remember it to be 0.7. That's how you answer that question. I'm going to just do this one more time from this point, because there's another way to do this that might interest you. Oh, actually, there's a third way, I guess. The way I started to do, it just would have been really, really messy. Basically, when you're deriving this formula, it's pretty messy. So it works to use the person who derived this work. We're allowed to use this, so let's use it instead of the way I just started to show you. But I'm going to show you now a third way, which you could do if you start from this one. I'll rub this out again. You can pause it and rewind and look at as much as you want. We could use conservation of energy. At least before these balls hit, you can. That's what I'm ignoring the balls hitting, because the problem when balls hit, energy or kinetic energy isn't conserved. There's all kinds of things happen. Noises, maybe it bends, it warps, anything like that. Momentum is. That's why we use momentum in collisions much more often. But we can use energy from this point to this point. So starting here, going to the point just before they hit each other, I can use conservation of energy. Let me clear a bit of room here. I think I'll probably still need... Yeah, I'll still need that force. What was it? The friction was equal to 3 mu. I'll keep that number there. That's a y instead of a mu. 3 mu. So in this world, what energy have we got? We have... oh yeah, sorry. This is the start of the world. This is the end of the world. There's another ball right there. I guess I don't really care about the second ball. No, this is fine. The start of the world, we're moving here, and the second state we're here. So let me actually rub this one out. Here's the first state. This guy's going 0, and we'll draw another picture. Hopefully this hasn't confused people too much. The second picture is the second state, where this is going 2 meters, and this is going 0. So what's the difference between this world and this world in energy? And we can use that to find mu. The energy in this world is a half m 0.3 v squared, 5 squared. And there's no potential energy, everything's on the ground. The energy in this world is a half. Again, this guy is, this guy's moving 2 meters per sec, 2 meters squared. This guy's not moving, there's no energy. This one's not moving, still there's no energy. So what's changed from this world to this world? Work must have been done against it in this case, because we want to slow it down. And that work is from friction. Work is energy. So we can look up the formula for work. It's simply F multiplied by distance. force over distance. So the work, we must have taken away work here, 3 mu over this distance. And that would equal this. That's the only difference between these worlds, the work done against it, the friction. And I apologise for how big the equation looks, but number, mu, number. We can just rearrange this and find what mu is. So let's do that. Mu is equal to this guy, a half 0.32 squared, minus this, a half 0.35 squared, divided by this, all divided by minus 3 over 1.5. And if you put all that into a calculator, you again will get 0.7. So you could do that last bit a couple of different ways. That was a really tricky question. That took me, okay, it only took me a few extra minutes, but I have lots of experience with these questions. But it stumped me for maybe a minute or so. I went down a wrong path halfway through the question. Yeah, really, it's quite difficult. So congratulations if you were able to get that. If not, hopefully this helped. If you need more help, put a question in the comments. I'll do my best to help you out even more. Oh, there's no units in this. The coefficient of friction is unless, so we're okay with that one. Okay, thanks for watching. Have a great day.